Hi, I'm Seth Rotenberger, and today I'm going to show you how to use the topology optimization feature in NX. Topology optimization is a fast and easy way to maximize the performance of a part with a set of applied constraints. Let's take a look at the process. In the graphics window, you can see I already have loaded several bodies into NX. I'm going to use these as my part and constraints. I'm going to start by entering the topology optimization function and create a study. We have the option of selecting the coarse to fine resolution of the study. The first thing I need to do is create my design space. Design space is the volume within the material layout. Aluminum is a good choice for the material in this application. The optimization constraint is where I can impose functional requirements of the optimal design. In this case, I want to set the maximum mass limit, and I put that at 1 kilogram. Next, I need to select the areas of the model I want to stay in or leave out. These holes need to be shelled so that the holes themselves are removed, but the area around it remains. The next hole will also be shelled, with a large thickness so that it can withstand the loads we will place on it. And finally, the body on top is kept out. Shape constraints can be added to the optimization to influence the size, shape, and topology of the optimal design. It can also be used to comply with manufacturing, geometric, and aesthetic requirements. To ensure the model is symmetric, I'm going to apply planar symmetry. I'd also like to set a limit for the minimum thickness allowed in the model. Using the minimum member size, I can set this to 10 millimeters. Moving on to the analysis constraints, the 4 bolt holes need to be pinned for the simulation to work properly. I would like to apply a torque on the inside of the larger hole. A bearing load is also applied to the larger hole, with a downwards direction. All the conditions for using the topology optimizer have been met, so now we can optimize the part. The study is now finished, so let's look at the results. We now have a mixed convergent body, which is a mesh body with some precise geometry. I want to see how the object responds to the applied loads, and I can easily see that when I animate the results. The largest amount of displacement is located at the largest hole, and the value is quite small for the model. I would also like to see the stress placed on the model, which I can easily switch between. Again, using animation, I can see that the most stress is located at the bolt holes. These results look good, but the part is pretty organic, so it would need to be 3D printed. Let's look at how we can add another constraint to make that happen. I'm going to clone the study so that it leaves all the constraints we have previously created and add it to another study. Let's head back into Shape Constraint and add Self-Supporting. I quickly specify the print orientation, and now we can optimize this study too. The second study is complete, so let's examine it. This new design would be much easier to 3D print, and it has a very similar displacement as Study 1. Let's take a look at these models side by side to visualize the differences. Again, using animation, I can see the different displacements on the models. The stress values also look very similar. Just to recap what you have seen, we have used the topology optimization feature on several bodies in NX. You saw me create a study with variable speed versus accuracy and make a design space while selecting a material. You then saw me set a mass limit and use construction bodies to keep in and out bodies. I then added symmetry to the part and made a minimum thickness. You saw me pin the bolt holes and add a force and torque to the larger hole. You then saw me inspect the results and then create a clone study with 3D printing in mind. I would like to thank you for your time and attention.